Welcome to the Deep Dive, the place where we take complex source material and distill it into knowledge you can actually use.
It's great to be here.
So today, we're jumping into software engineering, which, let's be honest, can often feel a lot less like engineering and a lot more like, I don't know, monster hunting.
That's a really good way to put it, actually. We're looking at some key research that talks about these projects, these catastrophic projects that start out looking so innocent.
Right, a simple tool, a clear objective for a database.
Exactly. But then they morph into what the sources call werewolves. They just become these cost-exploding, deadline-missing disasters that never, ever meet the original estimates.
I think every single manager listening right now has at least 3 of those werewolves on their books. And the question we really want to tackle is, why? Why does this happen so consistently? Why is there, unlike in almost any other engineering field, no silver bullet to just radically improve software productivity?
It's a huge puzzle, especially when you compare it to its neighbor, hardware. I mean, just think about Moore's Law.
The performance doubling every 18 months.
An absolute miracle. Hardware saw 6 orders of magnitude of improvement in 30 years. That's a genuine, undeniable technological revolution. It completely changed the landscape of cost and capability.
And what's crucial there is that it gave designers a choice, right? You could have dramatically better performance or dramatically lower price.
It was a clear exponential payoff. And software just has had nothing like that, no equivalent breakthrough, and we need to get to the bottom of why.
So what do the sources say?
Well, the reason, and this is profound, is that it's baked into the very nature of software itself.
The problem is the problem.
The problem is the problem. And the source material really helps us here by making a vital distinction. See, the programming part, the actual act of writing code, dealing with a syntax error, that's now, relatively speaking, pretty easy.
Okay, so if typing the code isn't the hard part, why are we still getting these disasters?
Because the real difficulty, the part that creates catastrophes, is all the conceptual heavy lifting. It's the analyzing, the designing, and then testing the whole thing with the user. That's where the really disastrous, the conceptual errors come from.
So it's almost like writing the code is just assembling IKEA furniture. You follow the instructions, you put tab A into slot B. The hard part is actually designing the furniture in the first place, based on a user vaguely saying, I want something that holds books and looks nice. And maybe it can be a desk sometimes.
That analogy is perfect. It hits the nail on the head. We're not failing at the mechanics anymore. We're failing at the concept.
Okay, so let's get into the core framework from our sources. This idea of accidental difficulties versus the conceptual essence. We have to understand what we've already solved to see the mountain that's left to climb.
Right. This is the core framework. So accidental difficulties are the problems that come from our tools, the technology we're using at the time. The essence is the inherent difficulty of just creating the solution itself.
The abstract problem.
The abstract problem. And what's fascinating is that most of the progress we've made in software history has just been about clearing away those old technological accidents.
So tell us about some of those wins. What accidental problems have we just wiped off the map?
Okay, so if you go way back, the invention of high-level languages, think C or Python or Java, that solved the accidental complexity of dealing with the physical computer.
So you didn't have to think about bits and registers anymore.
Exactly. Before that, you were wrestling with memory addresses and registers directly.
Yeah.
Now, all of that is abstracted away. It's basically gone for most developers. We solved the machine problem.
And what came next?
Then came interactive computing. That solved the huge accidental problem of slow response times, batch processing.
Oh, more punch cards.
No more submitting a stack of punch cards and waiting hours, maybe a day, to get an error message back. You get immediate feedback. It just dramatically sped up the whole workflow.
And then, of course, the integrated programming environments, the IDEs we all use now.
That's the third piece. They solved the accidental complexity of juggling a dozen separate programs just to write, compile, debug, and link your code. The environment is just so much more efficient now.
So having cleared all those historical technological hurdles,
the easy fixes, really,
we are left staring directly at the conceptual essence. That's the battlefield today.
That is the battlefield.
Okay, so we solved the mechanics. Now we face the real inherent challenges. And this conceptual essence is defined by 4 properties, non-negotiable properties. And these are the root cause of every project disaster. Let's start with number 1, complexity.
Right, and complexity here doesn't just mean big. It's about the unique structure of software. Unlike, say, a bridge or an engine, which have lots of repeating scalable parts, Software entities don't have repeating parts.
So it's not like building with Lego bricks where every 2x4 is the same.
Not at all. Every component is unique. It's highly specialized. And that leads to two massive issues. First, software can have an enormous number of internal states. Changing one single line of code in an operating system might unexpectedly affect 10,000 different parts of it.
Because it's all interconnected in this non-repeating web.
It's massively interconnected, which means software just doesn't scale in the way other engineering disciplines do.
That sounds like a constant game of whack-a-mole. You fix one bug, and 5 new ones pop up that you never could have predicted.
It absolutely is. And this complexity is what creates the communication problems on a team. It's the steep learning curve for new people, and it's why it's so hard to scale a solution without things breaking.
Okay, property 2 is conformity. And this is where software stops feeling like engineering and starts feeling more like diplomacy.
That's a fantastic way to describe it. Software almost always has to conform to the wishes of human institutions, laws, customs, business processes. And it has to interface with all these existing legacy systems. It almost never gets to dictate the terms.
So software is being asked to be a legal expert, a policy wonk, and an accountant, all at the same time, and bend to the will of all of them.
Absolutely. It has to conform because it's usually the last arrived at the party. Or it's seen as the most malleable part of the system, so it has to adapt to everything else. Our sources note there are no unifying principles, like physics driving its creation, just external, often conflicting human demands.
And that leads perfectly into property 3, doesn't it? Changeability. If it conforms to a changing world, it has to change constantly.
It's pure thought, infinitely malleable, and that is its greatest curse. Physical things change, sure, but software contains the function, and function is what gets hit first by any real-world change. A new tax law, a new business priority, a competitor's new feature.
And here's where we get that painful irony, the success paradox.
Yes, the success paradox. It says that successful software is the software that gets changed the most.
Because people are actually using it.
Because they're using it. They try it in other situations. They want new features. They demand new integrations. It ends up outliving the hardware it was first built for, and it's stuck in this constantly shifting cultural matrix of laws and user needs. If your software is good, it is under relentless pressure to evolve.
And finally, property 4, invisibility. Now, this one sounds less scary than the others, but you argue it's huge. Why is invisibility such a big deal?
Because unlike a physical object, a blueprint for a house, a diagram of a circuit, you can't see software. You can't just look at the finished product and instantly grasp how it all works inside.
You can only see representations of it.
Precisely. You can only represent it with multiple overlapping graphs and diagrams and documents. And none of them, not one, fully captures the whole dynamic structure. This invisibility makes communication between different minds incredibly difficult. It's almost impossible for one brilliant designer to hold this complex invisible thing in their head and then explain it perfectly to 5 engineers and 3 managers and 2 users who all need to sign off on it. That breakdown in communication is a direct driver of cost.
So the complexity, the forced conformity, the constant change, and this invisibility, that's the war we're fighting. And given all that, it makes perfect sense that we've been desperately looking for some kind of magical tech fix.
Some silver bullet.
Which brings us to the silver hopes. The technologies that promised everything but, well, didn't deliver that silver bullet.
Right. They delivered marginal gains, which are useful, but we were looking for that 6 orders of magnitude improvement.
Let's talk about object-oriented programming, OOP. For so many developers, that shift felt revolutionary. Are you saying that feeling was a bit of an illusion?
In the grand scheme of things, yes. Look, OOP is incredibly helpful. It reduces the amount of code you have to produce by bundling data and operations. It promotes reuse. It's great. But it mostly helps manage accidental complexity and only a tiny fraction of the conceptual essence. It wasn't that radical Moore's Law level shift that we needed to conquer the core conceptual problem.
What about artificial intelligence or expert systems? Surely they can automate some of this design work.
Our sources are skeptical. Expert systems are great for capturing the knowledge of top programmers in a very narrow, defined area. But when we talk about general AI today, it needs constant, careful guidance.
It can't just invent a solution.
No. And there's a great line in the source material. AI is open to hallucinations if you just let it run unsupervised. It's not some magic coder that can reliably understand a user's abstract changing needs.
And automatic programming, the dream of the future.
It's really only useful right now for highly constrained problems with very few parameters. things like AutoML and data science. The inherent complexity and changeability of general software just resists full automation. How can an automated system keep up if the requirements change every day?
We also tried to solve the invisibility problem with visual programming.
It helps a bit, but as the source points out, it only offers a limited view of an invisible thing. If your software has 10 million possible states, a visual diagram can only show you a tiny, tiny fraction of them. It doesn't solve the fundamental communication problem.
And the last, hope, just throwing more power at it. Better workstations, better tools.
They're welcome, for sure.
Mm-hmm.
They make developers happier and a bit more productive. But they are not magic. They just slightly improve the accidental mechanical side of coding.
So the takeaway here is crucial. If the solution isn't technological, if there's no magic fix coming,
then we have to change our strategy entirely. We have to stop looking for tools and start attacking the conceptual essence directly.
So if technology can't save us, what can? We have to shift our focus to structure, to management, to people. What are these promising attacks on conceptual essence that actually work?
Okay, the first strategy is so simple, but it's revolutionary in its impact. Buy rather than build.
Don't reinvent the wheel.
Don't even invent a spoke for the wheel. Every time you use existing, stable, commercial software, a module, a library, a whole semi-finished product, you are slashing the amount of custom complexity you have to manage yourself.
You're basically outsourcing the fight against conformity and changeability to someone who has already solved most of those problems.
Exactly. This means using general-purpose programs like a good database system instead of building your own data storage from scratch. Custom complexity is what kills projects. Buying it off the shelf reduces that complexity by orders of magnitude.
Okay, strategy 2. This one attacks the biggest cause of failure: getting the requirements wrong in the first place. This is refining requirements through prototypes.
This strategy goes right to the heart of the biggest risk we identified: the analyzing and designing with the user. You build iterative prototypes, not just to ship code faster, but to get the requirements right faster.
So the goal isn't really to deliver a product, it's to help the user figure out what they actually want before you commit millions of dollars.
You've got it. Prototyping attacks conceptual errors when they are cheap and easy to fix. It manages that inherent changeability because you're constantly cycling back with the user, folding in new ideas before they become disastrous change orders halfway through.
And finally, the most human strategy, and maybe the most powerful: find great designers. This really puts the focus on individual talent.
It does. Our sources are incredibly blunt on this point. The difference in productivity and quality between an average designer and a truly great one is an order of magnitude.
An order of magnitude, that's 10 times.
10 times. That is not a marginal difference. That's the exponential gain we were looking for. It just comes from human talent, not from a new technology.
So talent management is the real silver bullet.
It is. The action items are clear. Identify these great designers, develop them, reward them for the staggering impact they have, and crucially, structure your teams so that everyone else interacts with them. Let them spread their skill and knowledge. This directly fights complexity and invisibility by just applying superior brain power.
So let's bring this all together for you, the listener. This framework, it gives you the intellectual tools to understand why those projects, those werewolves in your portfolio, stall or fail. They're not crashing because of syntax errors. They're crashing against the conceptual essence of the problem itself.
Right. And it means success comes from strategy and talent, not from waiting for the next hot programming language.
Right.
The only realistic way forward is to proactively manage those 4 properties: the complexity, the conformity, the changeability, and the invisibility.
Buy what you can, prototype constantly to make sure you're building the right thing, and invest everything you can in your top design talent.
The solution is really less about writing more code and more about the careful strategic management of human complexity.
And to wrap this up, if we think about that big picture again, since good software has to be embedded in and conform to this constantly changing cultural matrix of laws and user needs.
And since successful software is the software that must change constantly.
It raises a really important final question for you to think about. Is the perpetual difficulty of software engineering actually a sign that the technology is flawed? Or is it just an accurate, unavoidable mirror of the fundamental instability and the ever-shifting requirements of the human world it's designed to model? Something to chew on as you manage your next project.